Today we are going to discuss MSR safety and safety in general. So I'm going to start with the lecture. I'm going to introduce the first lecturer today, Thomas Boisseau from Framatome, and he's going to give us an introduction to MSR safety. So the floor is yours.
Thank you, Sandra. Hello, everyone. I hope you can see my screen.
Yes, we can.
Thank you. So, hi, Sandra said, I'm Thomas Boisseau. I'm a safety engineer at Framatome, which is an industrial designer and supplier for nuclear power plants. And I have been working mainly on Generation 4 reactors and also on PWRs, mainly on the Astrid project, so French sodium fast reactor, but also more recently on a molten salt reactor within notably the SAMOSAFER project. So this lecture is an introduction to molten salt reactor safety, and this formation will rely on the fundamentals of nuclear safety, and we will often ask the question, how do these fundamentals apply to molten salt specificities? So that's the idea of the presentation. So first, I will present the safety objectives. And then we will ask the question, how do we respect these objectives when we design the power plant? So from this objective to the safety architecture, we will see that we rely on some main safety principles. And the question will be, how do these principles apply to molten salt reactors? And then at the end, I will shortly talk about the methodology, the approach that we use on SAMOSAFER and previously on SAMOFAR in order to implement safety at the design of the reactor. So, safety objective. Actually, there is one fundamental safety objective. I took the text from the IAEA document, Fundamental Safety Principles. So the objective is to ensure the protection of the people, including the public and the workers, and the environment from the potential risks associated to reactor operation. And mainly, we mean radiological risks. So protect the people and the environment. And to ensure that objective, measures have to be taken. First, to control the radiation exposure of people and the release in the environment. Then to restrict the likelihood of events that might lead to a loss of control of the reactor core or any other source of radiation. And restrict the likelihood is what we call prevention in the safety language. And the last point is that if such events occur, we have to mitigate the consequences. So the third bullet is what we call limitation of consequences, or also mitigation. We'll often hear about prevention and mitigation. So on this slide, I tried to represent these objectives with a curve. This curve is close to what we call a Farmer curve. That means that we represent for a given risk its consequences in function of its frequency. And on this curve, you can distinguish two different domains. If we have a risk with too high consequences and frequency, we are in the unacceptable risk domain. And for the risk with sufficiently low consequences and frequency, we are in the acceptable risk domain. And as you can see from the form of the curve, so the idea is for the most frequent events or risks, the objective is to have nearly zero consequences, or at maximum a very low level of consequences. But for very, very rare events, we tolerate to have higher consequences. So that's the idea of the management of the risk. And when we have a given risk, which is, for example, in the unacceptable risk domain, when we design our power plant, the idea is to implement some provision in order to do what we call prevention. That is the reduction of the frequency of the event, of the risk. For example, designing in order to improve the reliability or to prevent some specific risk to happen. And if prevention is not enough, we perform mitigation. That means that, okay, the risk, the phenomena happen, we have to manage its consequences in order to reduce the radiological releases at the end and to reach the acceptable risk domain. So to sum up, the objective to protect the public environment. For the different risks, we do prevention, so we reduce its frequency, and mitigation, we reduce its consequences. I hope that it's clear. So now we define an objective, and the question is how to design our power plant, our molten salt reactor, in order to respect that objective. And for that, we rely on some main safety principle, and that's that I'm gonna present now. And I will always ask the question, how do these principles apply to molten salt specificities? So in safety, we have three main principles for design to ensure safety. Actually, I put you some references if you want to go further. In these two documents from IAEA, you will see more details about these principles. So in fundamental safety principles, there are presented 10 safety principles, and in the safety of nuclear power plant design are presented more complete requirements for design that are important for safety. So if you want to go further, you can read some parts of these documents. So I can come back to what I consider the three main general principles to ensure safety. First, the fulfillment of the main safety functions. Secondly, the implementation of defense in depth principle. And finally, the implementation of barriers between the radiological material and the environment. So let's have a look further about the main safety function. So in a nuclear power plant, the safety implementation mainly relies on three functions: the reactivity control, the heat removal, and the confinement of radioactive material. So you can note that we talk also about radio protection of workers as a safety function, but I will not detail it in this presentation because it's specific. And at the right of this slide, I put a simplified design of that we use in the SAMOSAFER project. And we are going to explain the safety function, and coming back to this design, I will explain it a little bit later. So first, reactivity control. So you had some Newtonic lectures before, and the question is, what about safety consequences? And because you saw that there are a lot of specificities for molten salt reactor compared to solid fuel reactors. Before reading this slide, I just want to precise that the issue with the reactivity control is that if we have a strong reactivity excursion producing a certain amount of power that we are not able to remove, it may lead to consequences that we are not able to manage, and that's why it's very important to control the chain reaction. So for a molten salt reactor, we have some specificities very interesting from a safety point of view. First, it's important in the core area, in the area where the salt is critical. Actually, the salt is in a geometrical configuration, maximizing its criticality. So we do not have to fear that we have a compaction effect or somehow other effects that would increase more the criticality. So that is an interesting feature because when we are investigating the risks, we know that we have a maximum configuration, of course, at a given temperature and at a given composition, fissile material concentration. So we have a superior limit that is interesting to have in mind. Secondly, as you know, regarding the neutronic characteristic, we have a strong negative feedback effect on the molten salt reactor coming from density effect and the Doppler effect, providing intrinsic reactor stability. So when we design a solid fuel reactor, we also want to have a negative feedback coefficient. But this will enable us to have a natural behavior favorable in the first steps of the transient, but after it's just to have time in order to active some safety systems, for example, control rods, injection of boron, etc. But unlike solid fuel reactors, on molten salt reactor, we have a high negative density feedback coefficient, which acts instantaneously since the fuel is liquid and is very powerful. So this negative and instantaneous, almost instantaneous temperature feedback effect may have several consequences on the design of the molten salt reactor. For example, possibly there is no need of control rods in the fuel circuits. It asks the question. Also, it enables regular adjustment of the fuel salt composition. And what is interesting is that it includes the progressive filling for the startup of the reactor. Okay, so we have some advantages, but if we are in a situation where the reactivity control is really an issue, we still have a possibility to reconfigure the salt in a subcritical state by draining. So draining will give the salt another geometrical configuration in order to maximize the neutron leaks compared to the neutron production. So we will very soon reach a subcritical state. That could be interesting in case of accident that we are not able to manage in a critical state. So we have this possibility. And finally, I just want to mention that when we are talking about reactivity control, we have to have in mind also the local reactivity effects that we must study further. I mean, precipitation of plutonium, for example, or more generally of fissile material, freezing, or at the opposite, salt dissociation at high temperature. We have to confirm that in case of local effects, we can still manage the situation, because these local effects may lead to a reconfiguration in a more reactive configuration. Okay, so we can talk a lot about reactivity control, but I will stop here during this lecture. But if you have any question, please feel free to ask after the presentation. So reactivity control, now heat removal. What are the issues with salt cooling? Finally, considering the intrinsic characteristic of molten salt reactor, I really think that the realization of this function is essential, because as we just said, for a critical source, reactivity variations lead to a stabilization, but a stabilization at another temperature. And for structures or even for the salt itself, the temperature must remain acceptable in order to ensure their functions, to keep their integrity, their tightness, etc. So if the temperature becomes too high, we are not able to guarantee that the performances of the structures of the material will be still enough. So that's why it's essential to be able to remove the heat produced. That being said, there is no huge constraints on the coolant choice because there is no exothermic reaction identified with air or water. I don't mean that we can put in contact those fluids, but if we have a heat exchanger between some salt and some air or water, if we have a leak, okay, we lose the function of cooling, but there is no strong additional effect chemically. So that's interesting. Now, the management of the salt cooling. In molten salt reactor, we consider that we control the situation where the salt remains critical, because we will just rely on the neutronic feedbacks and will stabilize at another temperature. So the objective when we have an issue with cooling is to keep the salt in the fuel circuit as much as possible. And heat removal is ensured at that moment by intermediate circuits and safety systems connected to the intermediate circuit or the exchanger. So I will go back to the simplified design of SAMOSAFER. I don't know if you can see my cursor, but at the middle, we have the fuel circuit, and the exchange of heat will be at the right with the green circuit. And this green circuit, in normal behavior, will exchange its heat with the turbine, etc., etc. But if we have issues with the tertiary circuit, we have some safety safety system that enable the heat removal. For example, the purple line or the pink system just here. But when the salt is still in the fuel circuit, for the design that we use in SAMOSAFER, we still need at least the intermediate heat exchanger in order to perform heat removal. Okay, but if we are not able to remove the heat with the heat exchanger, the temperature in the fuel circuit will increase, and at a moment we will be we will have to drain or transfer the salt from the fuel circuit to some specific tanks. So if we manage very well the situation, we can transfer it to normal draining tanks that are not represented here. But it's a favorable case. And if we are not able to manage all the transfer, we will drain the salt in the emergency draining system, so in blue, just below the fuel circuit. In this system, the salt will reconfigure in a subcritical configuration, but still produces power, the residual power. And in order to remove this decay heat, we have some specific systems to remove the decay heat. And we look forward to have some passive system in order to have a robust accomplishment of the function. And if there is a problem in the emergency draining system, we can still spread the salt in the core catcher, where we have also a passive heat removal by air circulation, for example. But studies still have to be made in order to design the systems. So I talked about all these points. So what it is interesting to have in mind is that it's more comfortable to keep the salt in a critical configuration, because we still rely on the neutronic feedbacks, and that's why we have generally safety systems for heat removal implemented on the intermediate circuit. But in case of unavailability of this circuit, we have the possibility to relocate the fuel salt. That's the idea. And when we relocate the fuel salt, we are not critical anymore, so we just perform a decay heat removal. The last point that I would like to mention is that we have a multiplicity of residual power sources. We talked a lot about the fuel circuit, but there is also this fuel treatment unit where we perform salt reprocessing, and also the gaseous extraction, because in normal operation we extract the fission products, and fission products participate a lot to decay heat. So it's important to have in mind that we have to cool the fission products. Okay, so we talked about reactivity control, heat removal, and now confinement. Confinement, of course, there is the idea of confinement barriers, but it's the third principle that I would like to present today. So I will not talk about this in this slide, but we will talk about it a little bit later. The confinement, the idea is to have some barriers between the radiological material and the environment. What is interesting in the molten salt reactor is that there is an absence of pressure inside the containment. First, the process is unpressurized, and we have no exothermic chemical reaction. Of course, we'll have to study if we have, for example, water in the installation. If we have an interaction between salt and water, there may be additional effects creating pressure, but intrinsically, chemically, we have no pressure. And that's favorable because the pressure first is something that may push the source stem from the inside to the outside if the pressure inside is superior to the atmospheric pressure. And also it's something that may harm the containment and the safety systems that we use, for example, in order to perform cooling. If we have a higher pressure explosion, I don't know, we may harm systems, and it's an advantage to avoid this issue. Second thing, and important thing, it's about the continuous gaseous fission product extraction. As I just mentioned before, in normal operation, we extract the fission products from the fuel circuit to other areas of the installation. And this is very interesting in case of accident, because in case of accidents where we are not able to control exactly all the parameters, we know that the gaseous term source is in a low quantity. And gaseous term source, the fact that it's gaseous is important because it's the way where it is the most dispersible. If we have a solid, it will remain at the same place. A liquid, it will go into its recipient, but gaseous, it can go and diffuse everywhere. So it's more difficult to contain it. So it's an advantage to know that in case of accident, the quantity of gaseous term source dispersible is very low. But the counterpart is that we have a multiplicity of fuel material locations. And for example, as I just mentioned, in the gaseous extraction system, the salt extraction in the fuel treatment unit. So we have to manage the containments at different places of the installation. And because we often want to have some barriers inside other barriers, etc., the fact that we have multiple locations will make the analysis a little bit more complex, of course. Okay, so I talked about the main safety function, reactivity control, heat removal, and confinement control. Now we'll talk about the second principle, which is the implementation of defense in depth principle, which is a very important concept in safety. Before reading this slide, I just want to remind that defense in depth is a careful principle where we have a very humble attitude in the fact that we consider that okay, we designed our reactor, but maybe there is something that we underestimate, some risks that we forgot, some provisions that are not as reliable as we wanted. So we admit that maybe something that can physically happen, even if we implemented some provisions, this thing that may physically happen can happen, and we have to study what happens in that case. So it's that very humble attitude. And if I take the terms of the HIHA document, defense in depth consists in a hierarchical deployment of different levels of equipment. I will detail it a little bit later, but the idea is that we have some levels of equipment in order to maintain the effectiveness of the physical barriers. And the strategy for defense in depth is twofold. First, we prevent accidents, and second, if prevention fail, we have to limit their potential consequences. So for each level, we have prevention, and we consider that what we did as prevention is not enough, and we have to perform mitigation in order to limit the consequences, but also to prevent any evolution to more serious conditions. And another idea in defense in depth is that for a single failure, we have no propagation that will jeopardize all the levels that we implemented. Because if it is the case, we finally don't have the reliability, the total reliability that we want, and that may lead to large and frequent release that is not acceptable. That's why when we implement different levels of safety provisions, we are looking forward to have independence between the different levels. Independence means that the same failure will not make fail different levels. For example, we may look forward diversity between equipments in order to be sure that the phenomena that led to the failure of the first level would not lead to the failure of the second level. So different levels, prevention and limitation of consequences, and independence of levels. In this table, I put on the left side a table describing the different levels of defense in depth for PWR, so a pressurized water reactor. And this was a table from Msr Reactor Harmonization Working Group. And I will just detail very shortly the different levels. So Msr defines 5 levels. The first one corresponds to normal operation. So the objective is to continue to be in normal operation. The second level, it's about deviations from normal operations. It's not important from a safety point of view at this stage, but we have something abnormal in the installation, maybe little incidents. We are in anticipated operational occurrences, so little deviations from normal operation, level 2. The objective in level 2 is to have some regulations or limiting systems in order to go back to the normal operation, of course. But if these features are not sufficient, the deviation may convert in accidents. And that's the level 3 of defense in depth. In level 3, we have both situations due to postulated single initiating events or multiple failure events. For example, it can be due to a common cause failure on a kind of equipment, and we have multiple failures in the installation. So the third level is the level of accidents. So the safety analysis are in this third level mainly. The objective is to come back to a safe state. I will not precise exactly what is a safe state, but it's a state where the safety functions that we mentioned before are accomplished, first on the short term and then on the long term. So that's the objective. And the other objective is to prevent an escalation to a more serious condition. That could be the level 4. And the level 4 corresponds to what we call severe accidents. And for PWR, and for in a more general way, for solid fuel concepts, and severe accidents corresponds to the melting of the core. And that's what defines the 4th level of defense in depth. It deals only with melting accidents, core melting accidents. And if we are not able to manage core melting accidents, we consider that we may have some releases in the environment. And the level 5 corresponds to the procedures on public and environment that are taken by public authorities. So it's not the operator of the reactor that implements level 5 procedures. It's public authorities. So as you saw, it's important to recall that when we was addressing light water reactors with solid fuel concepts. That's not exactly our case for molten salt reactor. And I want to precise that the different evolution of defense in depth over its recent history mainly refer to the management of design extension sequences. That means the level 3B, multiple failure events, and the level 4 corresponding to core melting accidents. And it's important to precise that because we have several levels directly referring to severe accidents, the level 4 by definition, and the level 3A and 3B that must prevent core melting. And I insist on that point because these levels of defense in depth as defined by WENRA present some PWR specificities that cannot be directly applied to molten salts due to the liquid state of the salt. Thus, in order to define the safety objectives and to build the safety demonstration itself, for molten salt, we should examine how to implement defense in depth principle on a molten salt reactor, but in a meaningful way, taking into account the molten salt specificities. And that's the object of the work that we performed in SAMOSAFER. Okay. So we talked about safety functions, defense in depth. Now, very quickly, the containment barriers. The idea is pretty simple. It's to put some successive barriers between the fuel and the atmosphere in order to protect the public and the environment. On a solid fuel reactor, we usually define 3 confinement barriers: the fuel cladding, just around the fuel, the primary circuits, and the containment building. On a molten salt reactor, since the fuel is liquid, the usual first barrier, the cladding, has no direct equivalent. So the confinement barriers also, it's the same as severe accident, but also have to be defined in a meaningful way, considering the molten salt reactor specificities, including, as I mentioned before, the multiple locations of the system. So when we're talking about barriers, confinement barriers, for molten salt, we have to, it's an open question, we have to justify the number of barriers necessary. Maybe it will be at least 2, but maybe 3 are necessary. It's the main question for molten salt reactors. So we are almost sure that it depends on the design, of course, but the fuel circuits will be the first barrier. But there is a question: do we need a second barrier? And the last barrier, I think that it will be the containment building. But once again, it depends on the final design of the reactor. Okay. So I presented the 3 main safety principles in order to integrate safety at the design of a molten salt reactor. Now I will very shortly present you the methodology that we are applying on the SAMOFAR and SAMOSAFER projects in order to implement safety at early stages of design. So The question is how to make the link between the safety objectives and even the safety principles, what I just presented before, and the design. How do we make the link? So the International Generation for Forum, the GIF, developed a methodology called ISAM, Integrated Safety Assessment Methodology, aiming at integrating safety to early stages of the design. For molten salt, this methodology was thought in order to be applied for all Generation 4 technologies. For molten salt reactors, we still have some specificities, so we a little bit adapted this methodology, but the idea remains the same. So if I'm talking about this diagram, we have some objectives, some principles, some guidelines that we have to respect, and it's important to define this. But after, there is an iterative process between design and analysis of risks. So, okay, we have some guidelines. We make a design. From this design, we identify the different risks. Okay, these risks lead to unacceptable consequences. So we modify the design. The modification of design change the risk analysis. Maybe it creates some other risk. Maybe it reduces some other risks. We have an iteration. And finally, the objective is to have a safety architecture that is exhaustive, progressive, tolerant, forgiving, and balanced. So that's the idea of the methodology. On molten salt reactors, so we had work on design, and from safety point of view, we worked on the risk analysis, and we used two tools that I'm shortly going to present you in order to identify the different risks and what we can call initiating events. That means the events that may happen in the reactor, and where we study the transients and that are integrated to the safety analysis at the end. So in order to identify the different families of risk, we use two tools. So the master logic diagram, MLD, and the functional failure mode event analysis, FFMEA. I will just put you some example. This is an example of FFMEA. The idea is to take our reactor and to write all of its functions, all the functions that it ensures. And the idea is to go from the generic function, for example, to generate electricity, to the most elementary function. It can be every kind of possible elementary function, safety function, or operational function. At this stage, we don't mind. And the idea is when we consider only the elementary function, we ask ourselves two questions. What are the consequences if this function is not ensured anymore? And what are the causes that can lead to the failure of this function? So this first questionment enables to generate a first list of initiating events, and we can complete it with another tool, which is the master logic diagram. So with FFMEA, we have a strategy called bottom-up. We go from the elementary aspects to the more global consequences. With MLD, the idea is different. It's top-down. So we consider what we call a top event. For example, the failure of a containment barrier. In this example, it's the degradation of the core vessel. And from this top event, we are going to look forward to every phenomena, every cause of this risk, this major risk, and so on. From each phenomena, we are going to look forward to its causes, etc., etc., until to reach a very elementary reasons that may lead to the loss of the function. The combination of these two tools enables us to set up a list of initiating events for molten salt reactor. The results were quite the same, but we had some events that we identified thanks to the FFMEA that we didn't identify in the MLD, and at the opposite, but mainly it was a confirmation of the identification of the risk. That's it. I finished my presentation. Just before ending, I put you some references of work to perform in SAMOFAR on SAMOSAFER about safety issues. So if you have any question about these references, please feel free to ask at the end of the presentation, or maybe later. I'm still available. So that's the end of the presentation.
Hi everyone. So now it's 3 o'clock and we can resume the session of this SAMOSAFER online school module on MSR safety. I'm going to introduce our next presenter, lecturer, Evgeny Ivanov from IRSN, with in the spirit of this school of a more general lecture followed by a more advanced lecture. We will have a lecture on global regulatory environment.
Thank you. Thank you, Sandra, for this opportunity. Thanks everybody in advance for your attention. Before the lecture, I could give you some notes linked to the terminology and something like this. First of all, about SAMOSAFER. SAMOSAFER is not design. It's a European project. The goal, the main objective of this project is to study severe extent aspects of MSFR design. This is why we have to distinguish the object, intentions, and the subject to be studied. Then, talking about reactors, talking about nuclear technologies, we are meaning each time not the only technology as such, not the reactor as such, but also everything that is needed to deploy it. And what is needed to deploy it? Relevant infrastructure. Infrastructure has many positions, from science to industry and so on, but at the same time, it includes one point that I will talk about. It's regulatory environment. You can imagine what does it mean. You have many things that could enable the deployment of your technology. But there is also the something that put the constraints of development, so the limits that really dictates where you can deploy and where you might not deploy your ideas, and that is regulatory environment. What also we should take into account that regulatory environment exists. It exists and exists independently on our wishes and independently on our design concept. This is why we'll talk about it. Oh, sorry. Yes. We will start from the main statements, from what the object we are dealing with, molten salt reactor and molten salt technologies. Then we will talk about the basis of regulatory environment. It means that leadership, management, and so on. Understanding that everything in safety is a mixture between practical actions and decision-making process. Then we will mention briefly standards, safety fundamentals, and principles as they're seen and declared in EAA. I will give you also certain knowledge about the safety reports to be presented to technical support organization and then to the regulatory body. Safety case, what does it mean? And some actualities and some ideas about peculiarities of molten salt systems. Finally, we will discuss major factors and potential actions to be taken into account in terms and in context of molten salt technologies implementation and we will go to the conclusions. What should I note? That safety is a category of right. It's not technical category, it's not element of design. It is category of right that requires everything to have solid basis on reality. And also safety ideas and safety progress, unfortunately, is driven by accidents and by lessons learned and drawbacks from the major accidents we have had. Over here, I'm presenting the severe accident we know, the most known severe accidents and lessons learned from them. Because first of all, when we are talking a molten salt reactor, molten salt fast reactor, it is the status of this reactor is the very beginning of conceptual design. This is why it would be better to focus on such factors of safety that could jeopardize completely the project. So if we will not address those factors, we will not be able to even to develop and even to propose this idea. Let's come back to the lessons learned from different accidents. 3 Mile Island, co-melting, and after that event, it was decided to reinforce defense in depth. Over here, we should know that defense in depth, it's not the only prerogative of nuclear industry and nuclear safety. Defense in depth is known well. It's known well in different industry, airspace, car production industry, mining, something like this, military purposes. Everywhere, defense in depth was and is widely applied. But it has been adapted to nuclear safety analysis, nuclear safety studies, and nuclear safety from 1979. Over there, it was also underlined the needs to develop severe accident management guidance. Keyword is management, and the second keyword is guidance. So we are not talking about the analysis of accidents, but on analysis of how to manage the processes. How can we control and how can we turn our system to the safe state? Then a well-known accident at Chernobyl. In Chernobyl, it was underlined needs to increase and to follow the safety culture. Also, we saw the needs in off-site emergency planning. After Chernobyl, in all guidances, not just safety standards, but all guidances, leading countries and leading companies included the requirement to have the negative reactivity feedback, because you know that Chernobyl explosion was nuclear explosion due to chain reaction. And this is why negative reactivity and inherent safety properties are essential and even crucial for large reactor design and construction. And then last one is Fukushima Daiichi case, which demonstrated us the needs also to strengthen the application of defense in depth, to ensure the independence and reasonable redundancy of the safety measures and safety systems. Then this point is very important even for molten salt systems. This event demonstrated us the importance of ultimate heat sink, the availability of ultimate heat sink as the ultimate the measure, safety measure and safety provision part. Then, of course, we were talking about safety margins to be increased and to be, how to say, designed to comply even non-realistic hypotheses. Because what's happened there is just earthquake was much higher than it was expected, and this is why safety margins were not relevant to this extremely low probable case. So we might not rely on probability assessing the safety, and fighting for safety. Then, talking about regulated environment, I should note that from the very beginning of nuclear era, we began to talk about the safety rules, safety guidances, safety standards, and so on. Because of what? Because we did recognize that not the people, not the persons, but institutes should be on the first line of the safety. Institutes means organizations, I don't know, it's agencies and so on, but their role is very high and important. At the same time, their actions to be standardized, to talk one-to-one the same language. This structure, this system of relevant standards, guidances, and so on, is available on the basis of International Atomic Energy Agency. You can see the entire list of those standards. Some of them are relevant to our needs because we are not talking about the reactor. Safety relates to reactor and operation, to the real system. Nowadays we are on the paper base. We are on the our reactor exists only in paper, but we have to look ahead its design and its deployment, and to provide in advance sufficient information for a decision-making process. So we have to take into account regulatory framework, leadership and management for safety that does not exist but will exist in the future. We should think about research and safety for research for safety and regulatory purposes. We are now in the part of the sale of the research for design, but we also should take into account that it will be needed. Many things, you can see the slides are available. And the last point, it's interface with nuclear security. For us, it's essential because we are dealing with uranium-3, thorium, maybe plutonium, and we have to follow the security requirements. Why? In order to be not attractive for different for different malicious acts and actions. Then we should take into account that in our case, the role of simulations will be increased. So even tools and simulations would be impacted by exposed to analysis and assessment. We are dealing with multi-unit object by definition, and we will have unconventional source term because of appearance minor actinides, transuranium elements, and others elements that could form aerosols and make problems for us, not only fission products. Talking about molten salts technologies, we can see the variety of them and variety of the element of those technologies. We can design molten salt reactor with solid fuel, liquid fuel, stable salt, circulating salt, with different fuel, with different salts, with different spectra, with different application. Honestly, safety requirements and safety environment to be adopted to all the families of molten salt systems. At the same time, deep and very easy analysis of the potential, of the plausible reactors to be built demonstrates us that the degree of freedom for designers is not so high. In fact, it's limited because each reactor and each technology, it's a very expensive thing, and it might be designed and might be accepted not only if it will be safe, but also if it will address one or another challenge, impactive problem. It means that problem important for the humanity and problem important for sustainable development of nuclear industry and nuclear energy. In this case, what can technical support organization will see and what regulator will see from your design? This organization will not see the design in very detailed matters. They will see that we are dealing with fuel circuit. I mentioned that molten salt reactor, but it's molten salt reactor, it's everything. But nevertheless, it's active core, circulating loops, and so on. Fuel treatment unit, emergency draining tank, and storage of heat. Because of specificity of reactivity, discontinuity between reactivity and power control, this reactor will have this guy. What should we talk about them? First of all, they will be placed on the same site, so we will have different units. Each of those units has their own sources of threats and challenges. Reactor, clear. Fuel treatment, it is storage of very harmful materials and radioactivities, chemical compounds, and so on. Heat storage tank, it is a storage of heat and free energy. And emergency draining tank, attached to the molten salt reactor, to the fuel circuit. First of all, will include fueled salt from core, from all loops, from heat exchanger, and the volume of this core, of this the fueled salt in this tank will be at, between 3-4 times higher than the critical configuration in fuel circuit. This is why this salt to be diluted, and in this case, the volume of this tank will be increased, and we will have to find the compromise between reactivity, criticality issues. I mean, the reduction of risk of recriticality and heat removal. Because then bigger volume, then bigger surface, and the more complex there are more and more difficult to organize the ideal heat sink. So over there, we'll have to implement different safety standards in different ideas. First of all, safety standards for reactor, safety standards for nuclear fuel cycle facility, criticality safety, guidance, containment and heat removal system functioning. Everything to be there. We should take into account the recriticality issues for fuel treatment unit. It's clear because there are many fissile materials, and criticality excursion could, as generate energy, as directly expose the personnel over there. In emergency draining tank, the same thing. In fuel part, we should consider as power excursion as criticality excursion. Then we should take into account that we have a multi-unit system with common mode failures and so on and so on. So it's not so typical, our reactor, but as you can see, all standards are available. Then safety objectives and all the structure and all the system of the documents to be implemented when we are designing and constructing not only reactor, but the infrastructure and the basis for its implementation. First, we should admit that the risk management is a key point and the key action started from the very beginning of reactor design. So we should think about it before construction and even before the design studies. Then, all risks to be assessed, all risks to be analyzed, discussed, and so on. And third one, as I mentioned, that the way of risk addressing and risk precipitation is institutionalization of the risk and risk assessment and regulation. Safety has no borders, but not only geometrically or borders or country borders, but also safety has no borders along the design process. So each time we are thinking about the safety. Then you can see that many documents are well developed within AEA. They are developed on the consensual basis. So there is an international consensus on those structure. And nobody will change each one in favor of your reactor. So it's designed to be modified, it's designed to comply with the requirements, but not safety regulative environment. Nothing from standards and guidance will be changed. And also, don't forget, the safety communities rely on the warranted conservatism. So we have to be convincible, we have to be credible to demonstrate and to explain them why our system might be safe. As I mentioned, we have in the center of everything the safety fundamentals. First, responsibility. There are 10 fundamentals. Not everything relates and relevant to our needs, but something, yes. The primary responsibility for safety might rest with the person of our organization responsible for facilities and activities that give rise to radiation risks. So we have the main point is responsibility, and it's operator who is responsible. But operator should be informed, and its designer and vendor should prepare everything to inform operator and to give operator all means and all systems to manage the risk, to manage, to understand, to characterize the risk, and so on and so on. And then, role of government. Government establishes the regulatory body, authority, or something like this, authority committee or something like this, and government does it on the way to guarantee the independence of those regulators. So I think that everything is clear. The license to deal with the existing regulatory body and existing standards. Legal and governmental framework to exist before the deployment. And regulatory body as designer, as operator, also to be informed about the risk, the quality of risks, and opportunities to reduce the risks. But everything, as I mentioned before, should be based on the evidence. So it will not be the only declarations. Everything to be demonstrated and demonstrated in a clear, credible format. Leadership and management. As I mentioned, we are talking about the management and also leadership inside of this safety management. It's relevant to organization of operator and to authority and so on. So it's relevant to the building up of the management of the management structure or on the chart, management chart, and so on. I think that everything is clear. What I should note over there is that EEA recommends to use graded approach for safety analysis and safety assessment. Graded approach, among others, simply talking means then more risk, then more uncertainty, the more stringent regulation. And this is why risks and uncertainties to be evaluated and to be taken into account in building up of the regulation structure and regulation process. For us, it's important because we have a lot of uncertainties. We have a lot of non-identified risks because our feedback experience is limited. Then, justification of facilities and activities. What is important here, you can see the facilities and activities that give rise to radiation risk must yield an overall benefit, where the benefits must outweigh the radiation risks. What does it mean for us? It's something useful to optimize our design, because it's a source of the optimization. It's a source of going toward the informed regulation. Because in this case, we have to design and to deploy the system that will be better than before. For us, it's important, so it should be taken into account, and for designing the molten salt systems, we should identify where and why we would be better than others. Then, optimization of protection. Okay, it's just continuation of the previous fundamental, because it means that we have to apply ALARA principle. The safety should be higher. They provide the highest level of safety that can reasonably be achievable. For me, it's clear. Over there, we should analyze and judge the relative significance of various factors. How? The typical approach is PRT. Typical approach is expertise and expert studies. One of the problems we will face is that our experts are not, we have not so many experts because our expertise is limited. We had not yet the same systems and similar systems in operation. This is why we should combine those kind of approaches and a certain kind of theoretical analysis sensitivity studies and brainstorming as well. So principle number 6, and limitation of risk to individuals. It's clear it has been involved after Chernobyl, because before we were oriented in fuel cycle, for example, on the collective risks. It has been decided that it's no more actual, no more relevant, and this is why each time we are analyzing the impacts and consequences for person, for each individual. Principle number 7, protection of present and future generations. It's clear also principle. If we will not impose such a requirement, we will not answer the question on which distance, on which time we will guarantee the safety. And there is a risk that after 1, 2, 3, 10 years, our safety barriers will degrade, and so safety will not be provided. And then 10 years, 20 years, and so on, we came to the idea that everything to be protected on the long term. Why it's important for us? Because it relates to application of molten salt systems to transform minor actinides, transuranic elements, or to switch on the low waste fuel cycle uranium-thorium. Because in this way, we are increasing the global stability, and we are reducing the future postponed risks for the next generations. So it's just an element of optimization to be taken into account, to be recognized, and also presented in the safety assessment and safety studies. Then prevention of accident. It has been discussed before. I would like to mention that prevention of accident and accident management is the key point for safety assessment and for safety studies. Where talking about accident management, we are talking about the prevention of escalation of accident from one level to the next one, mitigation of consequences if possible, and achieving a long-term safe, stable state. Also, talking about accident, we should take into account that accident is a process. It's not just accident as it's all, the entity. Accident is a process that started from initiating event, continuing, and then ends with a safe, stable state. So we'll have to analyze everything and to manage the system, its trajectory along all the accident. Emergency preparedness, principle number 9. Over here it's also clear, but what I should note in the context of molten salt reactor, if even the probability and likelihood of emergency could be recognized as 0, we might not exclude it. We must demonstrate our preparedness to emergency, to severe accident, and so on, independently on the possibility, independently on our wishes of the accident progressions and so on. It is the first. Second one, source term. Typically, source term analyzed as source term made of fission products. In our case, it's not okay. It's not so, because in molten salt systems, we are reducing the amount of fission products in fuel salt. And this is why we have to focus not only on them, but other factors and other elements, minor actinides, as I mentioned. And the third point is multi-units layout. Multi-units to be considered not only as challenge for risk analysis and probability risk analysis, but also could imagine that we have a system. We would like to manage the severe extent to mitigate the consequences, but our environment, I mean that our infrastructure around the site degraded because of something, as in Fukushima. Because of tsunami, they destroyed everything around. Roads, plants, cables, electrical suppliers, and so on. It's typical case. And in our case, we are considering a reactor to be applied for heat generation, for electricity generation, for hydrogen production. And also inside of our reactor, we have a heat storage tank, we have fuel treatment unit. Everything could make problems for us. And this is why this aspect also should be taken into account. The last principle is protective actions to reduce existing or unregulated risks. Protection actions to reduce existing or unregulated radiation risk must be justified and optimized. So it's relevant to uncertainties, it's relevant to something that never could be regulated and never could be previewed and foreseen. That could happen with anybody. And after Fukushima, we saw it, that nobody could imagine either tsunami, either actions, either failure of team who was working on site, and so on and so on. This is why all residual risk and unregulated risks to be bounded, at least, and understood. Then, when designer, vendor, and applicant asks the license, it used to present safety report, preliminary safety analysis report, or final safety analysis report to regulator. The first reader, first organization that will read the safety report will be technical support organization as our RSM or NRC in the United States or something like this. And there are certain kind of judgments, certain kind of standards on that reports, but majority of them are relevant mainly to light water reactors. Look, the typical content of safety report: general description, site characteristics, structure, component, equipments, reactor, coolant. In our case, coolant and fuel are not divided. Engineering safety features will be instrumentation control, okay, electrical power, auxiliary system, steam and power conversion system. In our case, it will be power conversion system, not steam. Radioactive waste management, it's much more complex in our case. Radiation protection, universal. Conduct of operation, okay, it will be, except for certain items that will be taken into account, I will mention it. Accidental analysis, universal. Technical specification, quality assurance, all of them are relevant to the reactor in operation. In our case, in paper-based reactor, we have no ideas about it, not yet, but we should think about them. In molten salt reactor, talking about molten salt reactor, we could change a bit the titles and content of those chapters. Moreover, if you can see that fundamentals are fundamentals, they're fixed. Guidances, standards are standards, they're fixed. But the content of report is not fixed. With this report, applicant should be only convincible and credible and consistent. That's all. Applicant could present any report, but it should convince regulator and technical support organization that such report will present everything needed for safety analysis, for risk analysis, and risk quantification and precipitation. Inside of this report, we are analyzing safety case. Safety case is specific entity that comprises everything needed to understand the reactor performance and the system performance in terms of safety. It's very important to demonstrate it to decision makers to ensure that everything important has been taken into account. Inside of safety case, we are dealing with safety argument, safety cases is it, and safety case report, this one. So the content of safety case report typically includes scope, system description, system hazards, safety requirements, risk assessment, hazard control, safety analysis and tests based on evidence, demonstration of safety management system and explanation how does it work, developed process of justification, well, of course, conclusions. Everything, risk of failures, risk assessment approach, scenario, ranking analysis are incorporated inside in free format. Typically for PWR, for BWR, we have well stable formats, and people used to follow them because it's much more easy. It is harmonized on the basis of European Association of Regulators, VENRA. It is harmonized on the level of technical groups and technical reports of EEA, etc. But honestly, they are not fixed. They should answer the only one question. They should demonstrate the safety argument and protect those safety argument and then demonstrate to authority that safety goals are reachable and can be achieved. Then, coming back to defense in depth and changing a bit our understanding of defense in depth, I am demonstrating the rather old picture from WNRA meeting. Nowadays, it's accepted everywhere because it associates levels of defense in depth and new terminology on the states of our system. As I mentioned, we are considering functionality and function of our system and accident over there as a processes. And in these processes, we have different levels by severity of the accident and the severity of consequences. And those processes to be ended by safe state, where it is a question. The idea of defense in depth level, the idea of assessment of defense in depth came from NUREC, US NRC document from 1994. In the past, we are considering everything before accident. We are preventing accident prevention over here. We are doing nothing. We are trying to turn back reactor in any event to the normal operation. Then we are considering accident and we are switching on safety system analysis and safety systems functioning. Then if safety systems will be able to shut down reactor in safe and turn it on the stable safe state, everything will be okay. If not, we are containing radioactivity in order to prevent the large release of fission products and source term. Then we are talking about accident management, and then we are talking about citing an emergency plan. Everything to be taken into account, everything to be analyzed, but in the past, we were dealing with design-based accident. What does it mean? There's also flexible. Design-based accident is the accident that are analyzed and which analysis has been provided by designer. Then designer decided that other accidents are beyond design basis accident, and regulator considered those two parts of accidents and was agree or not agree with designer. The designer talked with systems available in nuclear power plant. We can manage those kind of accidents. And those kind of accidents we could not manage, but we can mitigate or something like this. And it's designer who defined which kind of accident we are dealing with. In our case nowadays, we are doing almost the same, but we mentioned that design-based conditions, 4 levels of conditions, design extended conditions, design extended conditions A without co-melting, with co-degradation. Condition means that everything to be analyzed, everything to be presented, everything to be assessed. So the new idea is to assess everything and to assess the capability to manage the accident on each level. Talking about the accidents and risks, we should come back to the very basic understanding of what does it mean risk and where it comes from. Typically, risks, we are analyzing risks, we are imagining risks as product of outcomes and likelihood. If they're independent, we can use logarithmic format, and in this case, we have those lines, the levels of risks, integrated levels of risks. If we have active systems in operation, there would appear correlations between observed outcomes and likelihood. And this is why this picture will not be will no more relevant. But at the same time, integrals would be taken into account. And integrals, when we are considering the probability and severity, looks like this one. Over there, we are preventing, we are trying to reduce probability, and concerning severity, we are mitigating the consequences. Then risks we are dealing with: simple risk, aleatory risks, epistemic risks. It means that something wrong in very basis of our concept, and unknown, fog of ignorance, and ontological risks. For our systems, ontological risks are elevated in comparison with others because we have not significant experience. Then, also I mentioned that many things are not fixed, are flexible, and one of those things is safety barriers associated with defense in depth. Don't forget the typical safety barriers for light water reactors that are started from fuel to clad to primary circuit to secondary circuit to containment are taken for information and given for information. You are not obliged to design and demonstrate this same, absolutely the same idea and the same ideology. You can first barrier establish here, you can establish it here, up to you. But it should be credible and it should be consistent and based on the evidence where you can demonstrate, we will be able to demonstrate the robustness of those barriers and fruitfulness of those barriers. Then we have 5 minutes to the end, and this is why I reduced my slides and comments on slides above slides. So the major factors to be taken into account when we are talking about molten salt systems. Design concept and operation models should be compatible with an existing safety infrastructure and regulation and regulatory environment. It's clear. So what is important for designer and for researcher? That is a concept to be adopted. Infrastructure might be the only enhanced before deployment of molten salt system. We are, unfortunately, we face the problem of limited feedback experience for large-scale molten salt reactor. And we think that the feasibility to be demonstrated progressively from small to bigger and bigger prototypes. Concerning first-of-a-kind low-scale systems, I don't see that we will face the problems because they would be regulated as research reactors. So it's much more easy to do it. The safety culture on the well-protected area where the excellence is high is much easier to be achieved, and this is why we will not have significant problem with them. Fuel circulating molten salts are multi-units object. It's clear because of details and peculiarities of its regulation and its control, physics inside, and because of the high temperature system intended to generate high potential heat for different even cogeneration and hydrogen production applications. Remaining uncertainties and unconventional options could increase a need for innovations, for new safety systems and new ideas. Okay, it's clear. And what is most, I'll say, delicate issue is that everything we know came from so-called committed parties, from people who had interest to design and to deploy the system. Unfortunately, it doesn't work for regulatory environment. We have to have independent point of view and independent source of information and source of judgment. And this is why addressing the demands of responsibility, resources provision, and radiation protection by institutionalization is the key point for safety. Applicant and licensee, all licensee, shall comply the authority decision where standards and guidance could be modified, but they are used by authority to facilitate the judgment. Regulatory body should have sufficient competence and should have available resources to perform the regulation. But competence might be developed by exchange of information, by sharing of information worldwide and even to a regulator. Data and evidences we are dealing with now are originated mainly by committed parties. So independence of judgment to be enhanced. How, it's another point, but it's also possible. And I think that the safety is inversed to the design in terms of industrial, industrially confident data. If for design we are trying to protect by royalty everything and all our ideas, in safety we should follow the inverse way, to open everything, to demonstrate the capability to provide the safety. Thank you.
So hello everyone. So welcome you back again. We are here now for the third part of this module 7 of the SAMOSAFER Online School of MSR Technology, and we will have a lecture on uncertainty quantification for safety calculation provided by Zoltan Perko from Delft University of Technology. Zoltan, the floor is yours. Doesn't seem, seems like he's not able to open the, can you just, we just wait for 1 second in case there seems like there is a small problem. Okay, Zoltan? Okay, now everything is, please, the floor is yours.
Yeah. Right. So hello, everybody. Good afternoon. My name is Zoltan Perko. I'm from the Delft University of Technology at the Reactor Physics and Nuclear Materials section. And for this presentation, I am going to talk to you about uncertainty quantification and specifically in regards to nuclear safety and nuclear safety calculations. So what I thought I'm going to do is just to give you a little bit of an overview of why we care about uncertainty quantification and what are the challenges of uncertainty quantification. Talk to you a bit about 3 specific groups of methods, you could say joint methods, spectral methods, and reduced order modeling, and then give you just some demonstrational examples of these methods on MSFR, so modern salt fast reactors. I think today you've already learned about quite a bit about safety and sort of the whole thinking about nuclear safety. So things like the regulatory background and the licensing background and the philosophy of defense in depth, etc. How that whole group of topics connects to uncertainty quantification is that for a long time, basically, when we thought about nuclear safety, the prevailing approach was conservatism. So what that meant is that whenever we, try to make a nuclear installation as safe as possible, when we try to figure out what would happen under certain accidental or off-normal conditions, then with the conservative approach, we always assumed the absolute worst at every single step, and then the idea was that if we engineer for these worst of the worst case scenarios, then everything would be fine. And around maybe 10 to 15 years ago, this has been gradually started to be replaced by what is called today the best estimate plus uncertainty, the BEPU methodology. The idea is that instead of basically just assuming the absolute worst, we should instead use the best estimates, the best knowledge, the best information possible that we have, and then just take care of the lack of knowledge, of the uncertainty, as a plus on it. So basically what we will always drive in these kind of safety assessments, whether that is at the design phase or whether that is at the licensing phase, etc., is that we would have certain quantities, certain responses of a reactor model that we are interested in. These are typically things like what is the maximum temperature of a cladding in a transient, or in an MSFR, what is the minimum soil temperature that you would have. All kinds of important quantities that have, of course, very clear connection to safety. And then we not only would want to know their values at nominal conditions, so you could say, okay, if everything is exactly as I suppose it is, then I can calculate what is the value of this response. But instead, on top of that, we always try to figure out the full statistical information about these responses. So we want, ideally, we would want to have their full probability the distribution function, probability densities, or at least we would want to know things like the mean value of a critical response or standard deviation, or things like what is the probability of basically being over some limit or being below some limit. And of course, this whole methodology basically requires two things. First of all, we need to have high accuracy, high fidelity models. This is also something that I think in the last module you already heard about. Maybe you remember my colleague Danny Lathauer's lecture on multiphysics models for the MSFR, which is all about how we can model everything in a reactor in general or in the MSFR in specific as accurately as possible. And then on top of that, once we have these high fidelity models, we need to have models so that we can perform uncertainty and sensitivity analysis on top of these high fidelity calculations. So why are we, or what kind of uncertainties are we worried about? Basically, you can think of the sources of uncertainties as anything that you would use as a data in your reactor. So these are all the material properties, typically cross sections, but also thermal properties, also things like heat transfer laws and heat transfer correlations, etc. These are things like geometries. So for example, if you think of a standard reactor, then you could think of the pins bending or some mechanical vibrations, thermal expansion, but you could also think of things like chemical deposits or crud that would locally change flow conditions, etc. Also compositions, you can think of either material impurities, or especially important for the MSFR, the whole composition of the salt, right? And that has all kinds of consequences to the neutronics or to the chemistry of the system. I put this in a bit of parenthesis, but also there are some uncertainties, of course, from the modeling choices that you make. So things like what type of discretization you use, what type of coupling scheme that you use. Obviously, these are not the same type of uncertainties, but they do have an impact on the accuracy of your results. And as I mentioned, basically what we want is that we want to know the exact relationship of how the important outputs from our high fidelity models, so these safety parameters or parameters that are important to safety, how do they depend on all the inputs and on the uncertainties of the inputs. And why I want to know these relationships is because, of course, we want to use this information to post-process and to derive things like identify the most important input parameters, maybe identify what type of properties need to be measured more accurately. Maybe we want to quantify exactly what is the probability of a certain failure to make sure that we can demonstrate that, you know, there is less than 1 in billions per year probability of something going wrong in the reactor. So that's sort of the whole methodology of how uncertainty quantification is very tightly coupled to nuclear safety in general. Now, why this is challenging, and I'm not going to read every single number here, but just to give you an idea. The problem is that, of course, for high accuracy, we want to use high fidelity models. And high fidelity models mean that you need expensive models that are very realistic, so they very accurately describe the real physics and the real chemistry, etc., that happens in reality. And you need very fine discretization. So if you think of a, let's say, an MSFR type model, then it would mean that if you just look at the neutron transport part, you would need something like on the order of 10,000 finite elements. If you have tetrahedrons with 4 linear basis elements, 24 angles, let's say 6 to 8 precursor groups, then easily what you see that the output that you calculate, that's around 10 million parameters for every single time step, right? So it's a very expensive model, just the neutron transport itself. Then of course we know that we don't only want the neutron transport, we always want all the physics that is happening in the reactor. So you would always have this coupled to at least thermohydraulics, but especially for the MSFR chemistry, etc. Just the thermohydraulics part, again, you do the same type of analysis. What is your spatial discretization, time discretization, etc. Again, you end up with numbers like 1 million parameters for every single time step, and depending on how the transient goes, of course, your time steps may need to be very, very fine. So that can be something like a millisecond, right? And as I mentioned, there are several other coupling available, because if the chemistry is important, if thermomechanical interactions are important, etc., all of those need to be taken into account. So this is why high fidelity model is quite complex, right? And what that complexity means is that it just takes a long time to calculate. So I think previously actually saw this number, but when we did exactly this calculation, then I think one single calculation took 4 hours on a 12-core CPU, right? So these are just simply computationally heavy calculations. On top of this, the additional problem, and what really the challenge for these uncertainty quantification problems is that these are not only many output systems, but also many input systems. Again, if you look at only the input parameters that you need to describe neutron transport, let's say you have a few hundred isotopes. Each of those have at least 2 or 3 reaction channels that are important. If you take an energy discretization of something like 50 to 100 energy groups, then you can calculate that easily you are in the order of tens of thousands of input parameters. And that's only the neutronics. And of course, you need to properly take care of about the correlations. And on top of the neutronic parameters, you have obviously the similar material properties, thermal hydraulic properties, etc. And why this really is a challenge is because what you will want to know is exactly how your high fidelity model behaves in this 50,000 dimensional input space. You want to basically know what is the value of all the parameters that are important for safety at every point of this 50,000 dimensional input space. And that is a challenge, because if it takes 4 hours on 12 cores to calculate one single situation, then if you wanted to properly sample such a high dimensional space, and you wanted to repeatedly calculate how your reactor would behave, that's very impractical, and for all intents and purposes, it's practically infeasible. And of course, this is exactly what we want to do when we do uncertainty quantification, but also for things like optimization. If you want to figure out what is the best combination of parameters, then again, you would try to basically find that sweet spot in this very, very high dimensional input space where your reactor performs the best. So that's sort of the general background. Now, just to introduce some formalism that I will use, I will always describe all these uncertain input parameters as a vector psi. This is a vector of n variables. That in reality, that can of course depend on how complex your model is, but typically this is at least in the hundreds, tens, thousands, tens of thousands. Since these are all uncertain input parameters, we assume that they are random variables and they follow a certain joint probability density function. And of course, we need to know, first of all, this joint PDF. We need to know if there are any dependencies between these inputs, if there are any correlations. This is the typical example, of course, for all neutronic parameters, right? Because there is a lot of correlation between the different group cross sections. And it's also something where already at the beginning, when you do any kind of uncertainty quantification, you should think about basically getting the best information possible. And what that means is that you want to know some really realistic, good, accurate information about not only the parameters, but also their uncertainties, because it's a, it's the garbage in, garbage out problem. If already you don't define correctly your input uncertainties, you cannot really expect that your output uncertainties are going to be realistic. Now, then of course, once we have our uncertainties, then we want to propagate these uncertainties throughout our model. I just put here a very general description of a model, where basically we have our independent variables as a vector x. Think of this, if you think just for neutron transport, then this x would represent spatial variables r, the energy E, and the solid angle omega. Right? These are all the independent input parameters. Then what you want to calculate with your model is the field U. So this is things like your flux field, or if this is thermal hydraulic model, this would be things like your temperature field or your velocity field, etc. And then I very generally just write the equations themselves with this general nonlinear operator n, that think of this as encompassing basically any sort of equation you could think of. And you can have, of course, some source terms on the right, and we have to have appropriate boundary conditions on the boundaries and initial conditions. Now, typically, what all of this math basically hides is simply a set of coupled partial differential equations. And why you always also have this C dependence everywhere is, of course, because some of the parameters, some of the numbers that are in this PDE system, they are random variables. So technically, these are stochastic partial differential equations. And then what we want to know is how the stochasticity in our input vector C basically propagates to either just specific responses, and then we want to know the, ideally, we would want to know the full dependence of any response as a function of the input parameter C. Most often this is very complex, so then we are happy with things like, at least let's know the mean value or the standard deviation, or maybe a risk probability that the value of a critical safety parameter is below or above some limit. And of course, again, if you really want to know everything, then of course you want to know the full dependence of the solution field on the input parameters. Now, this is kind of the general overview, and then I'm going to now give you 3 specific methods that can help you get and obtain this information. The first of them is adjoint methods. What adjoint methods do is that when I write this dependence, that we have some safety parameters R, and they depend on the uncertain input parameters C. Then actually, this is a shorthand notation for 2 different types of dependencies, because one can be a direct dependence on the parameter itself, and one can be an indirect dependence via the solution field. Let's say I'm calculating a temperature field, and the response that you are interested in is the maximum temperature in a transient, right? In that case, this response would simply be the maximum of the full temperature field. So if I want to know something like, okay, how does that depend on, let's say, a heat conduction parameter, then if my heat conduction parameter is C, then obviously the maximum temperature does not have a direct dependence on the heat conduction parameter, right? Because it just doesn't, it's not there in the formulation of that response. It obviously only has the dependence via the full temperature field. So what adjoint methods very simply do, they basically say, okay, if I cannot have the full functional dependence of this response, let's have the next best thing possible, a first order Taylor approximation. So let's at least locally try to approximate the real dependence as a linear dependence. And then the tricky thing is, of course, how we calculate this gradient. And if you look at the definition of the response, then you can just easily see that you will have to use the chain rule here. So you will have a direct term, which indeed just the dependence of the response on the parameters directly. And you will have an indirect term that is a dependence of the response as a function or via the solution field. And you can imagine that the really tricky thing is the calculation of this indirect term, because basically it means that I want to know how the solution of my PDE changes if I change any of the input parameters. So one way to calculate this is kind of a brute force way that is called a forward way, where I just say, okay, I can approximate this as a finite differencing. And it just means that I perturb individually every single input parameter, I recalculate, solve again the PDE, and I have the finite difference approximation for this gradient. You can imagine that this means that you solve 50,000 times the same very computationally heavy calculation. It's not really very efficient. So the beauty of adjoint methods is that they can basically give you this full gradient. So they can give you this derivative for every single parameter with one single calculation per response. I'm not really going to go a lot into the math of how adjoints work. I'm just going to really give you a very, very brief intro. Basically, the whole reason why it can work is connected to inner products and adjoint operators. Inner products you can think of, they're basically operations on a vector field. So if you have two functions, f and g, they both depend on the same independent variables x. You can think of the inner product between these two functions as basically the integral of their product. So if you think, again, I go back to Newton transport, then this would be your independent variables are spatial position r, energy E, direction omega. Then the inner product on this field would be that you simply integrate over volume, energy domain, and the full the angle, the product of the two functions. And then this special property of the adjoints is that if you have an adjoint operator that operates on one function in this inner product, then actually you can calculate the exact same inner product by having a different operator, which happens to be this a dagger, the adjoint operator, acting on the other function. If you don't really follow this too much, don't worry about it. Basically, it will mean that you can derive the adjoint of all the operators that you have in your original PDE, and you can derive a separate adjoint PDE, which is going to have the same type of PDE, just slightly bit different. But the really important thing is that this is very nice and works beautifully for linear problems and gives you immense amounts of information. The difficulty is, of course, that it gets progressively more complicated for any kind of nonlinear problem, because then you first have to linearize your problem. Luckily for us, a lot of the problems in reactive physics are actually linear. So if you think of Newton transport, Newton diffusion, they are both linear. All the important cases, source-driven, eigenvalue, time-dependent problems, even including some transients and burn-ups, they are linear. So you can use adjoint theory for all of these. And even the fact is, if you look at only the neutronics itself, a lot of the responses themselves are also linear. So basically what that means is that the Taylor approximation actually works reasonably well. Also, the types of responses that are easy to calculate with the adjoint theory basically are these reaction rate or reaction rate ratio type responses. And of course, for reactor physics, they are often exactly the type of responses we want, right? Because we often want things like fission to absorption ratio, or the group cross sections are all in this format, or we want things like power peaking factors or inhomogeneity factors. All of these can be written basically in a format that the adjoint theory allows us to calculate. And then for any actual use, the really nice thing is that if you look at most of the large reactive physics packages, all of this is beautifully implemented. So if you use Eranos, there is an adjoint package. If you use Scale, there is a whole SAMS module for it that allows all kinds of adjoint perturbation theory. If you use MCMP, there are the perturbation cards that allow you to use adjoint theory. So this is really something that you can reasonably easily use, even if you don't really understand the underlying math itself. And I'm just going to give you a feeling of why you should do this. The real nice thing about the joints is that it gives you immense amounts of information. As I mentioned, the whole nicety is that immediately you get the derivative with respect to every single input parameter. What that means is that if you look at a certain response, for example, let's say the K effective, then you get immediately the importance of every single isotope. Within every single isotope, every single reaction, and every single energy group. And you immediately get this information of how important that specific energy group, that specific reaction rate of that isotope is to the response that you are looking at. And of course, you can use this information to propagate the uncertainties. So for example, this is an example application that we did for a gas-cooled fast reactor. So it's not a molten salt reactor, but another of the Gen 4 reactors, where we looked at where does the uncertainty in the K effective come from. And then we figured out that the vast majority was due to basically inaccurate measurements of the uranium-238 inelastic scale. Now, of course, all of what I told you is very nice. One main limitation is this whole linearity thing, right? That it works nicely for linear systems and works nicely when the response itself is linear. And we know that, especially for safety applications, a lot of them are not really linear, right? When you have some very quick thermohydraulic transient, then yeah, things may not be linear. So sort of the next idea is, well, if linearity is not enough, then of course we should go to higher orders. And that is what spectral methods allow you. And I'm just going to go look into one specific way of spectral methods called polynomial chaos expansion, where the whole idea is that, okay, we are interested in these responses, R and the solution field U. With the joints, we made the assumption that they are linear, so we just did the first order linear approximation. We know that that is not good enough. So the next best thing is to say, okay, we are going to higher orders. How can we go to higher orders? We can go to higher orders by using some sort of a series expansion in terms of the uncertain parameters psi. You can think of immediately to the equivalence with Fourier series, and that's really what it is. In Fourier series, you have some kind of time evolution, and you say the signal, the real signal that you have, is very well approximated by sums of cosines and sines. And that if you then know how strong the different sines and cosines are, then you know everything about the signal. With spectral methods, that's exactly what we do, except our sines and cosines are going to be different types of basis functions, these CK basis functions, and the strengths are going to be these coefficients or modes in case of the full solution. So then the only question is, okay, how do we choose these basis vectors and how do we calculate the coefficients? And in polynomial chaos expansion, what we say is that we make a simple choice for the basis functions, that they are going to be multivariate orthogonal polynomials. What that means is that for every single input, I am going to have a different polynomial family and a different member of that different polynomial family, and then I'm just going to multiply all these different polynomials, one for each of the n input parameters. Why this whole polynomial family matters is that because it can be shown that depending on what the statistical distribution of a certain input parameter is, there are certain better choices of the type of polynomials that you should use. There is a whole scheme for this. I put it here if you are interested in. It's called the ESCI scheme of hypergeometric orthogonal polynomials. Really, what is important is that if you know, for example, for one parameter that is a normally distributed parameter, then you should use Hermite polynomial family for that. Or if you know that another parameter is uniformly distributed, then you should use Laguerre polynomials, and so on. Now, there's also just a small side note. There's also a way to handle dependent input parameters, in which case you can use some isoprobabilistic transformation, basically, to first transform the dependent parameters into a set of independent parameters, and then build your spectral model using those independent parameters. So then the next question is, okay, we identified now, I defined myself what these basis vectors are. Then we have to figure out what are the coefficients. And there are two ways to do that. One is the intrusive, the other is the intrusive, non-intrusive way. In the intrusive way, you do something very, very similar to what you do in standard finite elements, which is basically that you project your original PDEs onto each of the chosen basis vectors, CK. You integrate over your uncertain inputs, and you end up with a set of coupled PDEs that you would solve for these modes UK. This is exactly the same how you do finite elements, right? When for the field that you are solving for, you assume that it has this series expansion type dependence on X, and you just then project the PDEs on every single finite element basis vector, and via that you gain a big linear system to solve for the coefficients. Exactly the same thing, except there we are working in the X space, whereas here we are working in the stochastic space, in the space of the uncertain input parameters. The other way is via the non-intrusive way, and for all the safety calculations, basically this is what you want to do. Because of course, to do intrusive methodology, that would mean that you need access to all the underlying equations and all the discretization and everything, which is not necessarily that easy to do. And in the non-intrusive way, basically what you can do is either a regression type of approach or a numerical integration type of approach. I'm just going to go through the numerical integration. There, what you do is that you use the fact that you yourself have chosen these multivariate orthogonal basis vectors to be orthogonal. Sorry, and because of that, you can calculate the coefficients via calculating these integrals. And this type of formula, the denominator of this is very easy, because this is just the integral of the product of the two basis vectors. I chose these are typically known analytically. The tricky thing is the integral in the numerator, because here basically you need to calculate the integral over the dependence of the response on the uncertain input parameters. That's the thing that you don't know. So what you can do is you can use quadratures for trying to figure out this integral. Quadratures are nothing else than basically one way to calculate integrals. If you have some simple one-dimensional integral, you're trying to integrate this function f. There is some integrating weight p, which in our case would of course be the PDF. And then all that quadratures say is that you can calculate these types of integrals by simply approximating them by a finite sum, which says that you only need to calculate the value of the function at certain node values, disk Ci, and then each of them have a given weight. So for example, if you use a 3-point quadrature, that would mean that you have these 3 points, you calculate the function at these 3 values, they have certain predefined weights, you just weigh them and you add them up. And then, of course, there are different types of quadratures. There are Chebyshev quadratures, Gauss quadratures, etc. They are really minor differences. For this type of spectral methods, typically Gauss quadratures are the best because they offer the highest polynomial exactness. And then, of course, you should remember that these are not one-dimensional integrals, these are n-dimensional integrals. But for that, you can simply basically tensorize these 1D quadratures, and in multidimensionals, they are called cubatures. Really, all that means is that for every single dimension, you choose a different quadrature rule, and then you, for the multidimensional integral, you just make all the possible combinations. So if I have 3 points in one parameter, 3 points in the other parameter, I just make all the combinations. I calculate the function value at these 9 points. I use the corresponding weights. That is my approximation of the integral. And that already shows you that, okay, this is good, but it's also very costly, right? Because if you think of very high dimensions, and again, remember that originally these dimensions were easily in the hundreds or thousands or tens of thousands. Then, of course, if you take into account all the possible combinations with everything, then very quickly you end up with absolutely infeasible computational costs. And that's where sparse grids can help you. Basically, the idea of sparse grids is that when you look at these multidimensional integrals, you don't necessarily have to make every single combination of every single parameter with every other parameter. Instead, what you should do is that you should retain high-level quadratures, so basically a lot of points along each of the parameters. And then when you make the combinations, then you can combine lower-level quadratures, so basically quadratures with less points, and that is going to be accurate enough. And with this, you can already spare basically quite a lot of points. And you should remember every single point here is basically a solution of your full PDE system. The most computational saving, of course, you can get if you not only use these sparse grids, but you do all of this adaptively. So what that means that you would need to define some sort of error criteria that basically measures how important a certain region of the input space is. And then if you say that, oh, maybe in this top right region, I don't really have a good enough approximation yet of my response, so I need to add more points here. But maybe in this bottom left region, everything is very linear, everything is very easy. So then, of course, you would not want to base your computational time here. If you are interested about all these type of adaptive approaches, I put here the reference where you can look it up. Just a demonstration of how nicely this can work, especially for safety calculations, I show you 2 examples. This one is sort of a toy problem first. That's just a reactivity insertion. I think this was a point kinetics model that we did, where among others there were 2 uncertain input parameters. What is the magnitude of the reactivity insertion, and what is the effective delayed neutron fraction? And of course, as you can imagine, if you look at the maximum power that you would reach during such a transient, then of course this is going to be something very highly nonlinear, because as soon as your reactivity insertion approaches your effective delayed neutron fraction, then you are closer and closer to prompt criticality. So you are going to have an exponentially higher maximum power. You can easily see that in such a case, for example, joints would big time fail, of course, because the whole assumption of, yeah, the response is sort of linear, that's just absolutely not true. This is also very nicely represented here on the probability density functions, that even something like a 5th order polynomial was not exactly accurate enough, because the PDF was very highly non-Gaussian. It had this very, very long tail. And of course, for safety calculations, these are exactly the type of things that you are typically very much interested in, because that's where your reactor can fail. The other example I chose here is just to highlight how much adaptivity can help you. So this is an example of a maximum temperature during a transient in, again, this was a gas-cooled fast reactor. And what this very nicely shows that if you sort of do the standard uncertainty quantification method, the brute force way of just using some random sampling or Monte Carlo approaches, then even after sometimes thousands or even tens of thousands of calculation, basically the errors in your response would be much, much higher than what you can achieve with this kind of adaptive spectral methods. And what this means that, of course, yeah, they are much cheaper. You can get a much better view of how your model performs. We do have a open source MATLAB toolbox for this. If you are interested in it, quite a lot of the features that I talked about are implemented there. So feel free to give that a go. So this was the two methods, joints and spectral methods, and I want to finish off on sort of the crown jewel, which is reduced order modeling methods. Because what both the joints and spectral methods really typically do is that they give you certain responses, and they give you how responses depend on your uncertain input parameters. What reduced order modeling does, and I will specifically talk about proper orthogonal decomposition, is that it not only gives you these specific responses, but it really tries to give you the full dependence of the field. So how do you do this? You go back to your original PDE. Of course, when you would solve this numerically, you would always discretize this. So instead of your solution field, you would get some solution vector U that represents things like the coefficients of your finite element approximation, right? And you would have such a discretized system. And then what POD says is, and well, pretty much what all reduced order modeling say, is that you can approximate the full solution field or this vector field as, again, a series expansion where you have certain modes U that really capture the main, basically the main variability of your field, and they have different strengths, and these strengths depend on which part of your uncertain input space you are. And you can very easily see that this is actually completely analogous to what we did with the spectral methods. There we also made this assumption that we can just assume that the solution is some series expansion, and we have one part that depends on the uncertainty, the other part that depends on the field. This is exactly the same. The difference is that in spectral methods we fixed the uncertainty part. We just basically prescribed exactly what this dependence was, and then we tried to figure out what the coefficients or the modes were. And here instead we fixed the modes, and we will try to figure out what the coefficients are. How do we do that? Basically, we do that using singular value decomposition. What that means is that you produce a snapshot matrix, and the snapshot matrix is going to be just the solution, basically the vector that represents the solution at different input parameter combinations. You put that into one single matrix. You do an SVD decomposition on it. For all intents and purposes, you can think of SVD as nothing more than a matrix decomposition that gives your original matrix as a product of three separate matrices, where U and V are orthogonal matrices and sigma is a diagonal matrix. And then when you look at U, basically the columns of this U matrix are going to give your modes. So these are going to be the modes that represent sort of the really capture the essence of the physics of how your field can change because of changes in your input field. Some minor details, as I said, the singular values, they are in this diagonal, and basically the singular values are going to represent you how much of the overall information a certain mode contains. So typically what you do is you define some kind of threshold value, and based on that you say that I want to retain, let's say, 99% of the information, and that's going to tell you how many modes you need to retain. And then again, the question is, okay, now I have the modes, how do I get the coefficients? Again, there are two ways. You can do the intrusive approach, which is exactly the same as in the spectral methods. You would project all your equations onto every single mode, and you would solve the reduced equations. Or the non-intrusive way, where you use basically regression or interpolation. And you use that based on the exact values that you have in the V matrix. So one way that we did this, again, we went back to sparse grids. And why do we do that? It's because sparse grids are very nice and very computationally efficient way of sampling your input phase space. Now, because here we are using these Sparse grids for interpolation, you would choose a different type of quadratures. For the integration in the spectral methods, we use Gauss quadratures. Here we use basically just equidistant nodes. So that would mean that, you know, level 0 is just 1 point in the middle. Level 1 is 3 points in every single parameter. The level 2 is then the 2 points in between your previous nodes. Level 3 is again, you just add points in between your previous parameters. And of course, in multiple dimensions, you combine these points. And then for the interpolation itself, of course, you are free to choose any sort of interpolation. So if you know, you can try some radial basis functions, Lagrange interpolation, etc. What we found was one of the best ways to go is piecewise linear local basis functions. So basically, you just have, for every single point, you will have a corresponding piecewise linear basis function, and you build them up hierarchically. And this is, of course, how you do it in 1D. And then to get the n-dimensional interpolant, you would just tensorize them the same way that you do with the spectral methods. Why this is really nice is because, again, it can be computationally very efficient. And it allows you the same type of adaptivity that I showed you in the sparse grids, in the spectral methods. And of course, why we need that is because even if you use classical sparse grids, you still have this problem that if you have many, many dimensions, then very easily you end up in the situation where the number of computations that you need to do, so basically the number of times that you have to run your safety calculation, just goes exponentially. And then instead, if you use adaptive sampling, you can focus the sampling and you can focus the computational effort where you are still inaccurate. So for example, if you, let's say your true dependence of a coefficient is this sort of half paraboloid, then at the first level, you would just say, okay, I calculate this 1 point in the middle, and my first approximation is that everything is just constant. Then I can look at the child nodes, so these are the endpoints, and I look at, okay, how wrong I am. Well, clearly I'm quite off here, right? Then I will add, again, the local basis functions at these points. And these local linear basis functions, they are always just head functions. And then you can get a much better approximation like this, right? Then, as this is an interpolant, you are already accurate in all 3 points, but again, you are still a little bit off in the middle of the domain. Then again, you can refine your interpolant. You can say, okay, now I can add these local basis functions that are only connected to these points, and you can adaptively just refine your model as good as possible. You can, of course, extend this to multiple parameters. Basically, these are small details. Again, I put here the reference if you are interested in. What is really important is that via this sort of hierarchy of your points in the uncertain input phase space and properly defined error indicators, you can drive and focus your computational effort where it is really needed. And of course, that can give you massive computational savings. So just to show you an example, I'm going to skip over this. This is all has to do with, you can add the adaptive basis construction on top of your adaptive sampling strategy just for additional savings. And why it is, why we want this kind of adaptivity is basically because of this. This is an example of a 1D diffusion problem, just some 2 control rods, some different regions. And then you can see that for the same type of error, basically, if you use classical sparse grids, then you end up with, I don't know, tens of thousands of evaluations that you need. Whereas with this type of adaptivity, you can at least 1 or 2 orders of magnitude even decrease the number of computations. So to finish up, I'm just gonna show you an example for the MSFR. This is something you may have actually seen in the multiphysics simulation lecture. Yeah, we had a high fidelity model for the MSFR that couples neutron transport and the thermal hydraulics with precursor transport included. There are some details about the discretization. It's not really important. What is important, however, is that with this type of adaptive reduced order modeling, even for such a complex model, we were able to build in a very computationally efficient way very accurate models of full fields. So this is the result for the fission heat. This is the result for the temperature field, and this is the result for the effective multiplication factor. And you can see that even, I think we took into account 30 input parameters, and we could get these results with 60, 63, and 1,600 calculations. And of course, that also shows that the most difficult part of this is the K-effective, because for that we needed many, many more calculations than for the temperature field and for the fission density. But once you have these models, then of course you can achieve massive savings, because the original runs are around these 4 hours, and I think it was actually on 12 CPUs, whereas basically running the reduced order model is typically a fraction of a second. And then to finish off, these are just some nice results of the accuracy. So you can see that in the whole field, we can reconstruct with around 1 to 2 Kelvin accuracy, I think. We can derive exactly these probability density functions that we are interested in, because this is how you would try to figure out, probabilities of a failure or being over certain limits. And again, you can also use this for a similar type of sensitivity analysis that the adjoints allow. So you could look at, okay, which input parameter is most important for what response. One nice thing is that all of this works also for time-dependent problems, and it also works for adaptive sampling in time. That is always something quite tricky to do in reduced order modeling. Well, what we came up with is a method that can both adaptively sample in the parameter space, so the input phase space, and also in time. So that's what I thought to tell you. And if you have any questions, then feel free to ask.